involving x2, and then the known quantities ends up with minus 4. Third equation involving x3 ends up x3 is 15. Now we can do the back substitution. It involves the product of the diagonal decomposed terms and the upper triangular form here. When you multiply that out, you get an upper triangular form. This is the one that you can solve from bottom up. The first equation is particularly easy as you multiply this row times this column, because you get 5u3 equals 15, and so that directly comes out u3 equals 3. The next equation is this row times this column, and gives these terms where u2 is the only new thing to worry about, and you get that. Likewise with the third equation on top, you find u1, it comes out to be unity. And so we now have actually calculated the physical displacements here and get 1, 2, 3, which was of course a contrived problem. Now, what you might want to do is off to the side, run through these calculations in more detail. I have to admit that I've got to do these a little fast in order to get the lecture on, and it's pretty hard to slow it down so that a person would get every step. So make sure you're comfortable with this off on the side. We've spent quite a bit of time on the Gauss elimination solver, and that's really justified because of its importance. For completeness, though, let's now look at the iteration methods. Here we'll start with the Gauss Seidel iteration, and what we have is the standard nice structural stress problem, Ku equals F. We'd like to turn this into an input-output kind of problem so that we could guess the answer and then hopefully get an improved answer out. Now, how can we do that? Well, one way is an additive decomposition where we take the original physical stiffnesses and literally break it into two pieces, keeping the main diagonal terms on this K1 portion and then putting the terms above the main diagonal in a K2 portion. This still looks a little mysterious, of course. By the use of the property of matrix distributivity, we can then go into our equilibrium law and separate out those two terms here. Those are both in the nature of vector forces when multiplied out here. The one on the right, which is a little less accurate, you might say, will be now moved over to the other side where it will act as a correcting force on the true live loads. Meanwhile, the more dominant matrix with the diagonal terms is kept on the left. Now, it's surprising, but it's true that you can get an answer by assuming an initial value for the displacement field in the body here, calculating this correcting load, adding it to the live load, and progressing in this direction, and then finding the U solution and improved solution by solution of this simple triangular form, which we know can be solved from top down and involves n-squared floating point operations. So it's a fairly efficient process in terms of number of steps. The real question is, does it converge very fast? And the answer is no. And I'll give you a problem in the homework that will look at the convergence rate of such a process. A second iteration process to consider is Jacobi iteration. Again, we attack the standard problem with the nice stiffness matrix. And again, we do an additive decomposition by breaking the original physical stiffness into the diagonal term, which is dominant, and then the off-diagonal terms. We again, as in Gauss Seidel, move this correcting vector to the right-hand side. where it plays the role of a correction to the live loads. Then we make an assumption on an initial shape of the structure, a deformed shape of the structure through these displacements, and we calculate, going in this direction, an improved set of displacements. The cycle, of course, then is to continually reinsert the new improved vector into the original trial vector location. And I use these indices S and S plus 1 just to bookkeep on that, of course. Well, again, we have a problem in that this method might not converge, and it might take an awful lot of steps even if it does converge. Probably the most encouraging area, though, for iteration methods is in nonlinear mechanics, and in finite elements we're using Newton-Raphson methods a lot. Now, the new thing that those methods add is that they not only use information at this algebraic level, but they bring in some calculus in that they calculate slopes or gradients of the process, and then that helps point you in the right direction on your next trial, whereas you notice that these are all purely algebraic processes here. The first problem in our problem session will be a Soleski decomposition. Here I'm just presenting a simple 2x2 problem, two equations in the two unknowns. And you're asked to do this by Soleski decomposition. So the solution involves decomposing the original physical stiffnesses into this product of a lower triangular matrix times its transpose. This differs from the standard method in that on the main diagonal you do have terms that aren't unity. So on the left side you identify that there really are only three independent terms because of symmetry, the diagonal terms and then one off diagonal. Likewise, on the right side, the triangular matrix has only three terms. So it will turn out that in all cases this is a unique decomposition, that you have the right number of equations and unknowns. To solve it, we would start looking again at the upper left term in the stiffness matrix, which will be replaced on the right by this row times this column, which is L11 squared. Although a square root is involved, that one is trivial and we can do it analytically. The decomposition of the other two terms follows likewise. This one here is the equation for the lower left term, L21, and involves other things that are known. And you get L21 equals 2. Then the diagonal term in the lower right, which is L22, is found from this equation and comes out to be this time the square root of 2. So we've finally been caught by the square rooting that occurs in this Soleski decomposition. So I'll gather the results here, putting these in, and you see that this is the decomposition that results. A little simpler because you don't have the diagonal term involved, or the diagonal matrix, but more complicated because you do have the square root. Now we're ready to do the forward solution, and remember how we gather the matrix, the one part of the stiffness matrix with the physical unknowns, and call it a new intermediate vector x, shown here. Then we have a set of equations that unravels from the top down. The first equation is clearly x1 equals 5. And then the second equation I will bring up from the next page. I'll rewrite that equation I just wrote for you, namely this first equation with its result. Then we have here the second equation involving the coupled set, but we already know what x1 is, so we immediately solve for x2 and get it. Now with that we can go into the identity for the definition of x. This is the x vector. So our back substitution is to take this information and propagate it into this set of terms here, where here you have the L transpose and this is the U vector. That can be solved from bottom up, and we find the square root of 2 times U2 equals 2 times the square root of 2. When you solve that, which has been repeated here, you get U2 equals 2. Fantastic. Then the first equation, which would be row times column, is 1U1 plus 2U2 is 5. Solving that, you get U2 equals 1. And so we've come up with this contrived solution that's nice round numbers. But notice there were square roots involved in the process. Melosh was the first person that I knew that was blowing the whistle on this original Soleski decomposition. Back in 1969, I heard him giving talks around, and I heard him in California, and he had noticed that this was happening. It turns out the square root is not a trivial calculation on a computer. It has to be done by a series, for instance, or some other way. There's not a table lookup. There isn't any set of square root stored in a machine that it just looks them up. So doing a square root is like many, many floating point operations, and that's not done anymore. Let's now do a Gauss Seidel iteration. This is kind of fun, and you can watch the convergence process. Suppose you're given this set of equations, and it's 3 by 3. 3 equations and 3 unknowns, and we'd like to get an answer within 1% accuracy. Now, we know that the solution might depend a bit on the initial guess, so our initial assumed solution is going to be 1, 1, 1. We're going to try to exercise all of the degrees of freedom in the problem. Had we chosen 0, 0, 1, that might be a poor choice because you may have inadvertently made your vector perpendicular to the true solution vector, and so that it has trouble converging. So my tendency would be to make sure that I don't put a lot of zeros in it there. Now, another thing that people sometimes do in these diagonally dominant equations is to take the initial solution to be proportional to perhaps the inverse of the diagonal terms in the stiffness matrix. You know, judging that the stiffer the diagonal term is, the less the system will move. Now, that's not considering the load on the system, but could be kind of a problem independent approach that you could take. Now we'll do the additive decomposition of the stiffness matrix and rewrite our problem in a new form. Here on the left we have the remaining physical stiffnesses, but they've been robbed of the upper triangular part, which has been moved to the right side over here, and the upper triangular part appears. Then this is our new problem statement. We have a physical load minus this correction vector. If we put in our trial solution of unity in each degree of freedom, we can then multiply this out. When we do that, we take this row times this column, and that will give us, it turns out, a minus 2 and a minus 1, which is minus 3. That basically subtracts from this term. And the other two products are 0, so that these two terms are not changed, and we end up with this new improved force vector. We can use that to solve the remaining problem, which looks a lot like the forward solution of the Gauss elimination. You solve from top down, and I won't go through the details here. The first one's easy, that x1 is minus 1, but then the others you have to do a little work for. And you get the boxed in quantities on the right here. We take the solution that was just obtained to be an improved guess at the answer, and then we insert that into the right-hand side of our Gauss Seidel formula. So it goes in here is our first improved answer. We multiply to get this correction vector, which is incorporated into the load. Then we solve again for the x components. When we get those, we find this set of terms. And there is, you can tell there's quite a bit of oscillation here, that now we have a -2 and a plus 1.8. So things haven't settled down, certainly after 2 iterations. In fact, I'm showing a table here below where I give the answers after 10, 20, and on up to 110 iterations. You can see from the final set of numbers given that the answers are converging to to a 12 in this first location, and then 5.8 and 2.4. And of course, you could also get that same answer analytically by running it out. That might be a good side problem for someone to work out. But notice how the answer comes up rather slowly in some of these components and takes some while. In fact, it takes 42 iterations to get 1% accuracy in all 3 terms. It is common, though, for the convergence to occur at different rates in the different components. So there's often a most stubborn coordinate direction that converges last. But I think you can see that in a small problem with 3 equations, if it took 42 iterations to get pretty good accuracy, it would have been a lot cheaper computationally to do that problem by a direct method. That's not always the case, of course, and there are some problem classes where iteration methods like this, even in linear statics, would make sense. And I think the user would have to have some idea of the convergence rate of a whole class of problems. If it was perhaps fluid flow in pipes or electrical networks, you may get some class where it's a feasible way to